Welcome to Chapter 2, Complex Numbers, Algebraic Calculation and Applications. Throughout mathematical history, number systems have evolved to solve increasingly complex equations. Natural numbers gave way to integers when we needed negatives. Rational numbers emerged for fractions. Real numbers incorporated irrationals like square root of 2. Finally, complex numbers were developed to solve equations like x squared equals -1, introducing the imaginary unit I. A complex number z can be written as a plus ib, where a is the real part and b is the imaginary part. In the complex plane, the real part is plotted on the horizontal axis and the imaginary part on the vertical axis. The point AB represents the complex number z equals a plus ib. When we project this point onto the real axis, we get the real part rez equals a. Similarly, the projection onto the imaginary axis gives the imaginary part imz equals b. Special cases include pure real numbers when b equals 0, which lie on the real axis, and pure imaginary numbers when a equals 0, which lie on the imaginary axis. Let's explore operations with complex numbers. Here we define z1 equals 1 plus I and z2 equals z2 minus 0.5i. For addition, we simply add the real and imaginary parts separately. z1 plus z2 plus I of 1 minus 0.5 equals 3 plus 0.5i. Geometrically, this follows the parallelogram law of vector addition. For multiplication, we distribute terms just like with binomials. A plus ibc plus id equals ac plus ibc plus I of bd. Since I equal to -1, this simplifies to acbd plus ibc plus ad. The geometric interpretation of multiplication involves scaling and rotation. For any complex number z equals a plus ib, its conjugate is defined as z bar equals a minus ib, which geometrically represents a reflection across the real axis. The modulus z equals the square root of a squared plus b squared, which is the distance from the origin to the point z in the complex plane. For division, we multiply both numerator and denominator by the conjugate of the denominator. Zins equals z1 da z2 base bar by z2 minus bar equals zin z2 bar by z2 squared. This clever trick converts the denominator to a real number. Let's explore some important properties of complex numbers. First, the square of the modulus equals the product of a complex number and its conjugate. Z squared equals zz equals a plus ib aib equals a squared plus b squared. Geometrically, this relates to the square of the distance from the origin. Another key property is the triangle inequality. z1 plus z2 so z1 plus z2. This is easily visualized in the complex plane where the 3 points 0, z1 and z1 plus z2 form a triangle. The length of any side of a triangle cannot exceed the sum of the other two sides. The argument of a complex number is the angle theta it makes with the positive real axis. Every complex number can be written in polar form as z equals z cos theta plus I sin theta, where z is the modulus. Using Euler's formula, we can express this more elegantly as z equals z e thy theta. This exponential form reveals profound connections to trigonometry.